Hi, thanks very much for tuning in. This is another online locked down edition of Quantum Source. My name's Dr Adam Booth, and this comes to you loud and proud from the banks of the Leeds-Liverpool Canal. It's a lovely springtime evening here, and I'm sharing some of that spring sun with some of my new plants, and you might be able to see them up there. Seemingly doing pretty well at the moment, but it always fills me with a certain sense of dread whether I'm doing the right thing or not. Certainly my mum sends me loads of messages that say you really ought to be bringing the plants in because there might be another frost, and you never know when the last frost has passed and whether the plants whether they really know what they're doing or whether they are just lucky green idiots. But someone who's got some of the answers to that and can potentially set my mind at ease is Dr Laura Dixon from the Faculty of Biological Sciences at the University of Leeds. And in a second, we're going to be going and giving her a call. First of all, though, one of the main philosophies in Quantum Source was that fascinating facts are always best served with something refreshing, and today's recommended source is this, which is some sort of elderflower concoction that we made, done in honour of this old dude here, who's an elderflower tree who's also coming back into bloom. So get yourself something nice. I'm going to go back in and we'll give Laura a bell, and I'll speak to you soon. Cheers. So hello Laura, how are you doing?
Hi Adam, I'm not too bad. How are you?
I'm all right. It's a lovely springtime evening here, so I don't have a lot to complain about. And I was hoping you could set my mind at ease over some plant dilemmas. But first, recommend me a source for lockdown.
For lockdown, well, for me, I think it's got to be something the thing that we always go to in a time of crisis.
Red wine, vodka.
Yeah, it's got to be the old cup of tea, hasn't it? Really? Come on.
The classic.
I mean,
any particular kind?
Then red wine, then vodka. But start with tea. Just a good Yorkshire tea is fine.
That's the answer that I think we're all looking for. Nice one. So, what I was thinking was that, I'm pretty happy that I've got some plants out at the moment. I got some baby courgettes, got some beans out there. But I keep getting paranoid that I put them out too early and they're going to get damaged by the frost. So, should I actually be taking better care of them, or do they really know what they're doing?
Yeah, so that's a very interesting question. It is, in fact, something that I work on, and it's something that fascinates me. I would say you need to take a lot of care. So, yeah, plants that you've germinated inside, and then just putting them out. If they get caught by frost, they will die, I'm afraid to say.
That really wasn't the answer that I was looking for, but hopefully you can tell me why with your presentation.
I will do my absolute best.
Cool. Let's go for it. If you could share your screen.
Yeah.
Cool.
Yeah, here we go.
All right.
Okay. Yeah, so this is an area that's really fascinating to me for a number of reasons. And from an intellectual perspective, it's because, well, do plants know what's going on? If you put them outside all of a sudden, do they know what's happening? Do they know that they've been put outside in spring, or have they been put outside in autumn? And that's actually quite a tricky thing to work out, because day length and temperature signals are very, very similar in both of those seasons. And so it's intellectually interesting, but it's also very, very important from an agricultural point of view. So wheat. I work on wheat because it's our biggest agricultural crop in the UK. And it's a really good example crop to explain these sorts of questions and problems. Because one of the reasons wheat's such a good crop in the UK is because it has a long growing season. So we drill it or plant it sometime in autumn, and we go on to harvest it late summer. And that's really very unique in our agricultural crops, because normally, the growing season is much shorter. But because of the length of growing season, we get a very high yield. However, it becomes very apparent that for the kind of crop's growth and development, if we plant it in autumn and it gets confused and it thinks it's been planted in spring, it's going to go through all of its phases, its vegetative to reproductive transition and flower in winter, and therefore die from frost and the cold. So how the plant distinguishes this is really, agriculturally important. It's also important because it enables that transition to be a long and slow one through autumn and winter, and therefore that actually goes on to increase the overall yield potential that we get at the end. It's also important for other countries. So in lots of places, and I know it's hard for us to believe, but in lots of places, heat stress is a really major limiter on the agricultural crop. And so in those countries, the crop needs to be going through its transitions fast enough to avoid the really hot summers. And again, it needs to be able to know what it's doing to ensure that this happens. So there are two sort of major environmental cues that plants are using to do this. And the first one is day length. And so we all feel the effect of this. We know what this is. In the winter, it's very, very dark. And as we transition into spring, it gets lighter and it's all much, much better. And it's a very clear signal. But it's a very clear signal because we know what happened the day before. We know that the day before it was very, very dark, and the next day it's a bit lighter. And so for plants, they don't have the same conscious memory that we have. So how are they going about working out, well, right now, today, is lighter than the day before? And the way they're doing this is actually using a system that's very similar to a system that we also have, and that's called the circadian clock. So the circadian clock is like an innate timekeeping mechanism, and it enables us to keep basically a roughly 24-hour rhythm. And this 24-hour rhythm would maintain even if we were put under constant light or constant darkness. And what the 24-hour rhythm enables is that, for us, our general bodily functions, such as, when we wake up, when we feel hungry, our hormone cycles, they're all maintained within, distinct rhythms. For plants, it means that this 24-hour rhythmicity enables them to be able to anticipate when dawn is coming, based on when dawn was the day before. And it also enables them to time in different developmental triggers and different biological processes. And so this is really important for enabling the plant to know when to go from being vegetative and just growing and producing leaves to being reproductive and making flowers. And the way it does this is actually it combines the circadian clock basal rhythmicity with its 24-hour period with protein stability. And so what I mean here is, so in this image you can see that under short days, the rhythmicity of this particular gene called CO or constans is low during the light and then goes up during darkness. The exact same rhythmicity is maintained under long day conditions. You can see again it's low during the light, but because day length has changed, it's now going up during light as well towards the end of the day. And the difference here is that the protein that this gene encodes, constans, when it's made, is actually dark liable. So it gets broken down in the dark. So when in long days it's being expressed and being made in the light period, it can then go on to signal and have its normal function to trigger flowering. And so this is actually a really clever mechanism to be able to keep track of day length and the changing day length, because it's controlling both like a 24-hour rhythm with protein stability, and the two integrate for the plant to know how long each day is. And interestingly enough, exactly the same mechanism is used for plants which actually use short days as the trigger to flower. And so things like rice flowers under short days, and it's just using the inverse system of this, but is the same output. So, it's really cleverly done. However, that only answers part of the problem, right? Because the plant is able to track day length, and the protein stability is maintained under light, and then it's degraded in the dark. But actually, the day length in autumn and the day length in spring is very, very similar. And the changes are so small and incremental that it's not enough for a plant to be able to distinguish, actually, is this autumn or is this spring? And being able to make this distinction is absolutely essential for, for our crop plants, such as winter wheat, but also for, little annual plants that have a very short life cycle. They germinate in spring and they finish by the end of summer. And so what plants are actually doing is using a slightly belt and braces approach by also integrating another signal. And that second signal is temperature. Now, temperature is a tricky environmental signal to work with. As we well know, there is no on and off state. And so unlike light and dark, it doesn't go, we can say, oh, it's hot and cold, but that's just part of a big, long continuum. In addition, there isn't really any kind of guide temperature for saying, okay, it's spring, it's going to be 12 degrees for 4 weeks, or in autumn, it's going to be 11 degrees for 4 weeks. That's not how temperature works. It's a very fluctuating signal, and there can be some really, really strange years where, you just get your Indian summers or absolutely, freezing winters. So how do plants actually use this signal? And they use it in conjunction with photoperiod. So the two are very, very interlinked pathways. And we know that plants are using temperature as a signal because we can see that when it fluctuates abnormally, we see very clear effects on the crop's yield. So as I say, it's a very fluctuating signal, and that's across the season, but it's also across the day and the night. And so to use temperature per se would not work. And so what the plants actually do is they integrate temperature signals over a long amount of time. And regarding identifying seasons and knowing which season they're in, they're actually integrating temperature signals over many weeks. And so this process is called vernalization. And what's happening is when the plants are drilled or germinate in autumn, there's a break on immediately, a developmental break that can only be lifted with a prolonged amount of cold. And by a prolonged amount, I'm talking weeks and weeks and weeks. For some varieties, it's months of cold. And when they've experienced this prolonged amount of cold, then that developmental break is lifted and the plant goes on to be able to go into its reproductive phase. So this process is called vernalization, and quite a lot of it is known about vernalization in different species. And it's interesting because different species have recruited different genes, but the overall kind of molecular mechanism of vernalization is actually quite well conserved. What happens is initially, as low temperatures are received, or perceived, I should say, the gene expression is dropped. Or I should say, gene expression changes. In some varieties, it goes up. The change in gene expression. And then as temperature is perceived to be low for a continued amount of time, then epigenetic regulation on that particular gene occurs. And so this is really the memory of winter that's happening now. So these genes are being epigenetically tagged and locked into the expression state that they're in. So it's important for the plant that epigenetics is used because it wants to be able to re-wipe this system in the next generation. So when seeds are formed from this particular plant, they don't want to have a memory of winter. They want to learn that afresh and new for each generation. So that's why it's an epigenetic memory. It's wiped when a new seed is formed, and they go on to then go through the same adaptation process. And so as I say, this is quite a belt and braces approach, and it enables the plant to know that if it's being put out there in autumn, it can sense, first of all, I haven't received the cold signal, and therefore day length has no effect. But when it then receives the cold signal and the day length matches with what it needs to go into a reproductive state, then these two things enable a very rapid growth in spring, and that's what we see. And that's why plants they're not waiting for a spring signal. They sort of already had most of their signal during winter, and then it's really like a bursting forth. And very, very similar thing is happening in trees. And so I just thought I'd mention this because it is so similar. The trees in autumn, as you know, form these buds, and these buds actually then become like actually biologically isolated from the rest of the tree. And they're just sitting there waiting to be chilled. So for them, it's in biology, it's called the chilling requirement, and they're just waiting for winter to feel the chill. And once that chill has been met, they then will go on to burst. So once again, it's very much that it's the winter signal that's controlling this and not the actual signal of spring. But it coincides with the arrival of spring. And that's sort of like the critical thing. And so I said somewhere in the middle there, well, what happens when there's very strange years? I think we already know the answer to that, the fact that very strange things occur. So, you know, buds do break out of season if there's particularly warm or particularly cold set of temperatures occurring. And this really is another area that's very interesting for me because it relates to climate change and what we can anticipate the changes to be and how we can kind of work to be able to prevent them, to kind of sort of at least avoid our major crops doing anything that's particularly peculiar. And so just to sort of wrap up, there's one additional aspect which I think is really cool about how plants go around being able to predict kind of conditions and be able to sense responses. And that's the fact that when they are going through the process of vernalization or the tree buds gaining the chilling requirement, they're also triggering responses which enable them to then, you know, be better prepared for winter. So for our crops such as wheat, when it starts to change the expression of those genes involved in vernalization, that also triggers the expression of genes required for frost tolerance. And so that process enables acclimation and really enables the plant to anticipate the coming winter season, as well as anticipate the coming spring. And I think that's a really cool system to have in place. But sadly, it does mean that little plants, little seedlings that have been grown on windowsills and then get popped out are not in the best condition to deal with the frost. So yeah, I hope I answered your question.
So I have to be a better plant dad, in short.
I think that might just gives them a little bit of time to adjust to conditions. Right.
Okay. So my mum's advice was sound. Thank you very much, Laura. Okay. So I did have a couple of questions as well, Laura, and I know I asked about seedlings, and you told me about trees. What about bulbs? Because I plant out bulbs in November, and then I see them sticking their shoots above the ground in January. And I think they've gone too early. So I go around like chucking a load of compost back on top of them. Should I actually be doing that, or do they know what's going on as well?
So a lot less is known about bulbs.
Okay.
But I would say that from what I know, I wouldn't be covering them up again.
I'm ruining my plants.
The thing, I imagine that they are also responding to the amount of cold. So there will be a mechanism there which is enabling them to know when to come through. Okay.
Right. Well, again, I've got to refine my plant dad skills.
Yeah, sorry. Bulbs are not my area of expertise, but I would say don't.
They know what they're doing. Okay. The other one I was going to ask is kind of how are we actively adapting plant strains to climate change then? Is it sort of selective breeding or?
Yeah, so at the moment and for the foreseeable future, GM is absolutely prohibited in the UK. And so it is selective breeding, but it's basically we work on a basis of identifying target genes in the lab and testing them out under a number of different conditions, and then identifying how we can trace those into elite varieties. And so by trace them, I mean that identify the particular genetic allele, so the particular version of that gene that's enabling a more robust temperature response, and then developing a molecular marker to be able to use it to watch it go through subsequent generations. So it's selective breeding.
All right.
It takes a very long time.
Absolutely, yeah, cool. What I would say is that if anyone watching this has any questions for Laura, then you can either tweet the Quantum Source Twitter account, you can find us on Instagram. Laura can then see those questions, and I think she'd be happy to answer anything that you want to answer.
Yeah.
All right, great. Well, with that, I will. I'll say bye, Laura, because I've got some plants to go. I need to go and sort out. Great.
Excellent. Okay.
Thanks very much for your talk.
Bye.
See you now. Bye bye.
Oh, dudes, how can I make it up to you? I've been really bad. I'm really sorry. I just like extra food, extra water. I'll probably bring you in if it gets real cold. Just forgive me, right? I have a lot of sucking up to do to these guys, so I'm gonna love you and leave you. Do look out for other quantum sources in this lockdown period. We'll be keeping you sane and educated all in one go. Look out for the Quantum Source Twitter feed, the Quantum Source Instagram feed. But these have been my badly treated plants. I've been Dr. Adam Booth. This has been Quantum Source. You've been great. Stay well. We'll see you soon.